code, and I will start the video, everything. All right. So, did everyone read this document already? Yeah, as it says here, this is only a draft, so you can expect it to change somewhat, but hopefully not too much. So we want that you will start on the project the 3rd of May, and you will finish 2nd of June, so you will have roughly 1 month on the project. Yeah, I plan to have one 25-minute session with each student where you can ask some questions regarding the project if something is not clear, or you want some feedback on something. And yeah, I plan to do this the 18th, so it's roughly in the middle of the project. Yes, for the 8th in this project, we allow you to use any 8s, but what we mention that's important is that you must cite any sources that you use, and you cannot like the only thing that you're allowed to do with other people or students is to discuss the papers, but you cannot get any other help from different people. So you're not allowed to let someone write a paragraph for you or make a figure for you, or do any work on your report, but you can discuss the papers if you like. And we have yeah, at the University of Stavanger, we have rules for cheating and plagiarism, and hopefully none of you will attempt to do something like that. Yeah, and then I put a limit on the report to 3,000 words, which is roughly 6 pages. And this is the maximum, so it's not like this is not the minimum. Sometimes people can be confused. This is the maximum, so don't write more than this, and if you're able to write less and still include everything, then that's great. So there's no, you will not get any extra points by writing more, and in fact you will get a deduction if you pass this limit. So please try to keep it somewhat concise. But this is regarding the words. But if you include figures, illustrations, graphs, pseudocode, tables, something like that, then this is a plus for your report or project. Yeah, you will deliver it in a PDF format on Canvas, and I will somehow figure out the best way to do that. Probably sometime in the next the foreseeable future. So what are you expected to do for this project? So as I probably mentioned it a few times before, that we want that you are very familiar with the Paxos protocol and the multi-Paxos. and you also did this in your labs, and you're now working on more extensions of the protocol, which is again increasing your knowledge about how it works. So this is really the fundament that you will need to start this project, and you will use this as a basis to compare with the two other protocols that you are assigned. And what I will do is that I will give you one research paper for each of the protocols. And there might be, you might have to search the web on your own for supplementary material. And this can be, YouTube presentations or presentations elsewhere, or different research papers. So if you're able to find more information, then that's great. But please remember to always cite what you use, and you must also cite, for example, if you find some information on Wikipedia or even on YouTube. If you take some information from our YouTube presentations, then put that into your report that you found this information in this and this YouTube presentation. Just so you don't have you don't run any risk to be caught for plagiarism. Yes, and the idea is that you will be given two additional consensus protocols, and I've put this at the end here in group 1 and in group 2. So I will it will be the plan is that we will do a kind of randomized draw in a lecture, next lecture, or a lecture before the project starts, where each student I will be we will draw randomly, so that each student gets one paper from this group and another one from this group. And the idea is that none of you will have the same combination. And yes, I want to do it randomly so that it will be fair for everyone. Yes. Okay, so what is you're expected to do? So I outlined 5 points here that you kind of is expected to put in your report. So the first thing, succinctly describe both the Paxos and your assigned protocols, including the assumed system model. So here I wanted you to describe in your own words, with illustrations if needed, how your protocol works, what's the main things that your protocol does and solves, and what's the purpose of this protocol. Number 2, clearly identify differences between the protocols. And of course, this is not a difference in the name or a difference in name of the phases and stuff like that, but this is more higher level, how the protocol works. If, for example, if you're given 2 consensus protocols, then what's the differences in message exchanges or time delays and such things. Point number 3, difference in similarities between the underlying assumptions, failure model, and system model. So this is more that you're able to describe or identify what's the assumptions for each of the protocols, because in every research paper and every protocol, they will kind of assume something where what is the system where this protocol is being used. So you should be able to find out that information and find the differences between the protocols. Then point number 4, you must be able to say something about the pros and cons of each protocol. For example, overheads, performance, any other metrics, use of performance enhancing techniques, and it can be more. And lastly, I want that you identify some applications, real-life applications of the protocol. Where would it be appropriate to use this protocol? Yes. And for grading, I put these bullet points here. The citations, it's an important one. Clarity of explanation, that you can explain all these bullet points in a clear and good language. You use visual aids, figures, plots, etc. It's a correct analysis and discussion, and that your report is well formatted. So please use LaTeX. Well, I didn't put it as a requirement that you must use LaTeX, but this is a good tip for you. And it is also a good training for your master thesis, where you should probably also use LaTeX. Well, it's a good tip. So that's that so far. This is, as I said, only the draft, which will have some changes in the future, but at least now you see the main idea. And please, if there is any questions or something that is not clear, we can discuss it now, or you can message me later on, and we can I can answer them. So if there's no questions regarding that now, I wanted to jump into the Bitcoin presentation that I promised to you. Is everybody with me? I was surprised there was no questions about this exam report. I thought that you would have at least one question, but it seems fine. All right. Yeah. The thing is that I put these papers here, but of course it's not like you must or I expect you at all to read all these papers. You will only need, you will be assigned one from each group, and I will not do this assignment before the start of the project. So probably the lecture that is right before this date or on this actual 3rd of May, we will just do this assignment, and I plan to just use like random.org or something like that. Yes. Okay. So yeah, I've shared this with you all, and you can comment if there's any questions. So about this presentation, you must just stop me if I'm going too fast, because now I have been working on this Bitcoin and blockchains for a long time, and maybe I can like subconsciously skip some things that you might not have or be so familiar with. So please just stop me anytime, and I can go into more details. But the idea about this presentation is that I will give you a kind of a very high level, I would say, introduction to blockchains and Bitcoin from a systems point of view. And it's not a theoretical presentation, and it's also not a presentation that concerns itself with the economics of Bitcoin or cryptocurrencies. So I stole this presentation from Hein, and we will go through it, and I hope it will be understandable. So this presentation, it's from 2019, I think. So all the numbers here with the Bitcoin prices and yeah, stuff, hash rates and things like that, they are a little bit outdated, but still the point comes across. And if you especially a few years back, then everyone was kind of talking about blockchain, and they wanted to do everything on blockchain and use it for everything. And it was kind of on the rising to the top here with on the Gartner hype cycle. But here is blockchain, and here is blockchain for data security. So it was a lot of focus in the industry about blockchains, and they even, Gartner even have a separate hype cycle for blockchain businesses. And you can see there's just a massive amount of things here for banking, investment, blockchain in government, Internet of Things, decentralized autonomous organization, smart assets, and blockchain in education. A lot of things that people are suggesting that they can use blockchain for, and a lot of these projects are in the early development stages. And And that's that. So yeah. Yeah, how does Bitcoin kind of work? What's the components? It's a peer-to-peer network of miners, and remember from before we discussed about peer-to-peer networks. It means that everyone is equal. Anyone can join. It's a decentralized network, and all the transactions are recorded on a public distributed ledger, which is what we call the blockchain. And Bitcoin was kind of the first blockchain that supported consensus. Yes, so Bitcoin, it was invented by Satoshi Nakamoto. Oh, sorry. And the original white paper, it's called Bitcoin, a peer-to-peer electronic cash system. And it's actually a very short paper if you want to read it, and it's not so difficult to read. Well, it's kind of a mystery who created it, but anyway, he has a big account, or big or a lot of bitcoins, and you know they well, here it's calculated out that it was worth $6 billion, and in 2017 $19 billion, and probably now with the recent price spikes it's even higher, so it's you know, astronomical sums. And yeah, as you know, that the price fluctuates rapidly. But I guess here it's this is only up to until 2016, but I don't even know what is the current price. Is it up to 40,000 for one Bitcoin, or yeah? Anyway, I think it's a lot higher now. Yeah, there's a price spike for 17,000 or 18,000, but I think currently it's even higher. So one of the first incidents that was that happened in the crypto economics, it's the Mt. Gox incident, where someone was able to steal a large amount of bitcoins. As you see here, someone stole up to 850,000 bitcoins, and you know, if each bitcoin is worth $40,000, you can do the math that it's a lot of money. So yeah, Vahid said here it's currently 58,000. So you know, it's a lot. And of course, everybody is thinking that oh, why didn't I buy when the price was much lower? But yeah, and there was also well, it's currently is and was used before for this Silk Road application, where you could buy drugs and other criminal services. And well, from the screenshot you can see here the they're selling two pills of Xanax for 1.5 bitcoins, and from the recent price that Vahid mentioned, it will be maybe $80,000 or so, or 90,000. So yeah, this is of course a screenshot for a long time ago, but it's kind of ridiculous to imagine how much the prices have increased. We need to explain how it works. We need a few preliminaries, the hash functions, and the hash-based data structures and digital signatures. All of this is kind of things that we looked on in the lectures, and the basic hash function, or the cryptographic hash function, takes a arbitrary string or byte input of any length, and it's a one-way function, runs to the hash function, and then generates a fixed length output. Hein put an example here. He wrote a long paragraph here and piped this to the SHA-256 hashing function, and it generates this long string hash string, which starts with 4FCE, and he has a period here at the end, but when he changed this to asterisk, you can see that the hash value completely changes. So now, instead of starting with 4FCE, it starts with F77F, and yeah, basically all the bits are or a lot, most of them are different. That's why that even if you change only one character in the input, then the output will seem completely random. And of course, there is no way to go from this hash string back to the original text. So the main important properties that we will need to explain is the collision-free property, the hiding property, and the puzzle-friendly property. And these words, or the properties here, they go under different names, but these are the names that are used in the book that I shared with you on Friday. So anyway, the collision-free property, it's easy enough that if you have two, or you cannot find two values so that they are different, but they are the hash value of them are the same. So it should be computationally infeasible to find any two values that have the same hash value. But at the same time, since we allow an arbitrary length input and we are hashing to a fixed length, we have kind of an infinitely large input domain, but a fixed size output domain, which means that there must actually exist an infinite number of collisions. So it's like it sounds like a paradox that you want a property that it's infeasible to find any collision, but at the same time you know that there is an infinite number of collisions. But anyway, this is how it works. And you can read in the cryptographic papers about hashing function if you want to know more. Because of this, we oftentimes just compare the hash value of two things, and we assume by that if the hash value between these two inputs are equal, then the original input value is also equal. We can use this to, for example, when you download a file from the internet, you can check its hash value, and if the hash value matches what the original author said to you before, then you know that your download was successful and there was no one that interfered. Yes. So yeah. The hiding property here, it's about a property that's needed when you mine the blocks. You probably heard about mining. But the idea here is that you take the original input, the X, which can be the transactions that you want to put in the blockchain, and you put in a random value, a random number, for example, which is often called a nonce, a number used once, and even if you knew only the nonce or only the input value, it's not feasible to find the other value. Because as I showed before, then every time you put a nonce, you concatenate it with the original input, the resulting hash output will be completely different. So that's that. And you can use this to commit to a value. For example, you can write something. You can write the hash of something on the blockchain, or even in a newspaper or in a public blog post, that you can, if you write only the hash, you can say, for example, I will tell, in 1 year, I will give you all a secret message, and the secret message has this hash value. Then if you can, in 1 year, you can write that secret message with the matching hash value, then everybody can kind of trust and know that you knew that secret 1 year ago, because you couldn't possibly generate an exact value that matched that hash. So that's why you can, using this cryptographic hash technology with the nonce, you can commit to a value that you will reveal in the future. And it's kind of explained as an envelope here that you commit to a message with a nonce, and you publish only the hash value, and that's the envelope. But when you want to open the envelope or reveal it, you publish the matching message and nonce, and everybody can verify that the commitment matches the origin. The commitment matches what you just published, message and nonce. So yes. So the next property, puzzle friendly. It's a property that says that it's not possible to find or given an output value y, you cannot find the x value that's needed to produce the y value. So here it's talking about that the puzzle friendliness implies that no solving strategy is much better than trying random values of x. So when it comes to mining, the mining slides will come a bit later on, but when you're mining, you want to target a specific output value, and the only way to do that is to try random input values. So if you have a target y, and this target, it can be, for example, you want that the output has four matching or 4 consecutive 0 in the start of the hash output, then all the possible strings which has these 4 characters set to 0 will be your target. And you have your k, which is the transactions, and then you need to mine this x. So the x is the nonce, and you will try all the possible different values of x until you reach a hash that's in this target that you had. So if the y is set very large, for example, if it's set here to all n-bit strings, it's trivial because every output will be in the target. So the first time you hash something, it will be in the target. But if the y is set very narrowly, for example, in the extreme case to only a single element, then it's basically impossible to solve the puzzle. So what they do in the proof of work blockchains is that they set this to some difficulty where they can expect that the solution will be provided within some time limit. Yes. So what's the other? So now we covered the hashing functions, and now we'll go to the hash pointer. And you probably all used a hash pointer in your programming in the lab. But anyway, the idea is that you use this hashing pointer to point to some piece of data, and what this allows you is that upon retrieval of the data, you can run the hashing function again to confirm that it's matching the key that you expected, so that you know that nobody could tamper with the data. Yes. So the idea of blockchains is to link these hash links together in a structure like this, where the block header, as they say, so the block header here it's a pointer to the previous block, and the next block is pointing to the previous one, and so on. So what this allows you is that whenever something is changed, or if something is changed in any place in the chain, then this change will be detected from in all the next blocks. So if I change this data here, then I will have a new hash value here, and this will give me a new hash value here, and it will give me a new hash value here. So this error propagates through the whole chain. Right. So yeah, it's a tamper evident log, and in the example I just mentioned here, that if someone alters this data, for example, they can alter it with a false statement saying that they have a lot of money, for example, or they can do any write any data here. This error will or this tampering will be detected in the next block, and then in the block after, and so on. So that's why that the kind of so if you wanted to to change this data, you needed to also change the next block and the next block and the next block. So the longer the chain is, the more difficult it will be for you to change the block. So that's why oftentimes the blockchains, they have a confirmation time where they say that after, for example, 6 blocks or 5 blocks, then the value is considered committed, because once the chain grows into a certain length, then it's becoming completely infeasible that someone will be able to create a fork, which they call a fork, which is longer than the original chain and has different transactions. Yes. Yeah, so inside these blocks here, the data here, it's usually organized as a Merkle tree, where the transactions that are inside each block is organized as a Merkle tree. And yeah, I'm sure you are familiar with this. So it works that you start with the input data on the lowest level here, and then the hash value of each of these data elements are added to the first row of blocks in the Merkle tree, and then the hash of these two are to the next level, and the hash of these two are to the next level, until you reach the root, and you have only one hash value, which will be the root hash of your tree. So what's the benefit of using the Merkle tree? Well, one advantage is that you have what we call the proof of membership, or also called inclusion proof, which allows you to prove that some data was in fact part of the tree, or in this case the block, using a logarithmic number of hash values. So you don't need to provide the whole tree, but you can provide the root and the path down to your data. And if you're able to provide this, then the recipient can have some confidence that you that your transaction was part of the block. So, for example, if I wanted to, if I can draw for you here, if I have this block here, and I want to prove that this is part of the root, what I need to send to a recipient is that I need to send this one. I send this one. I send this one. I send this one. Right? So that if someone have this one, and so we have this hash value, this hash value, this hash value, then he can know that this transaction was part of that root hash here. So this is an alternative to sending the whole tree. Yes. So digital signatures next. Oh, sorry. Here. All right. Yeah, we also covered this in the lecture, but the idea here is that only one person can sign with the digital signature, and this is the one that can sign is the one that have the private key, but then everybody can verify using the public key. So yeah, yes. Usually what you do is that you actually don't sign the actual message, but you digitally sign the hash value of the message, because the public key cryptography doesn't support too large of an input, so you only sign the hash value. Yes. So yeah. First off, you need to generate a secret key and public key, and you keep the secret key, also known as the private key. Same thing. And you sign using the secret key, and you verify using the public key. So, as I said, in most or basically all real-world applications, then you will not sign the message, but the hash value of the message. So probably it should be also updated here in the slide that this is what you will do in almost every case. Yeah, it relies on the same assumptions as I mentioned before with the hashing functions, and an adversary cannot forge the signatures. All right. So how are people identified in the Bitcoin or the blockchain networks? So you in these networks you will have a public key and a private key, and your public key serves as your identity. So that you are it works in a way that, of course, no one can tie this public key to your own person, but in the blockchain network, this is how people will identify you, and only the holder of the secret key or the private key can write any message associated with this public key. Yes. And since it's a peer-to-peer network, you're allowed to make as many identities as you want, and you can do this in a number of seconds. And if you would imagine this, now you started with reconfiguration protocols in Lab 5, and if you imagine that there was an attacker that could create new Paxos servers in your network, and he could create, for example, 50 Paxos servers in a few seconds, then he could obviously take over your network and make the network behave in a bad way. And this is what we call a Sybil attack. So that since participants are able to create new identities and as many identities as they want, then the network needs to be resilient to this type of behavior, so that the consensus protocols cannot be a majority. Because if it was only a majority, then an attacker could just create more and more identities to gain this majority. Right. So yeah, so we can look at two naive implementations of blockchains, and the first one is the Goofy coin, and in the Goofy coin, by the way, these coins, they are covered in the book that I mentioned to you also, so you can take a more detailed look in the Mastering of Bitcoin book. So in this Goofy coin, he creates a coin and he signs it with his secret key, and he pays to the Alice user, and he signs the transaction, and then Alice pays to another user, but she can also do this attack, the double spending attack, where she's using the same coin and paying to someone else. So she pays to Bob, she signs that, and she can also pay to Chuck, he signed that. And in this protocol, the Goofy coin, there's a big double spending vulnerability, which is a fundamental challenge that needs to be solved in all cryptocurrencies. So a more sophisticated approach is the Scrooge coin, and he is so clever that he's instead using a transaction to keep track of all the. No, he's using a blockchain to keep track of all the transactions, and well, he's of course he's Scrooge, so he's signing everything himself. So he can mint his own coins because this is his protocol and he signs it. And it works in a way that coins can only be consumed, but in the same block, then you can create or mint new coins which are unspended. So I believe this is how it works in Bitcoin too, that you coins or transactions can only be spent once, but if you overpay, then you will use the residue to create new unspent coins. Sorry, my throat is all too dry. Anyhow, yeah, so this is the immutable coins, that they can't be transferred, subdivided, or combined, but you can consume the coins and create new ones. But yes, the Scrooge coin, it works great, but it has the big limitation that it's owned by one central entity, and we of course wants to decentralize the thing. So what will we do about that? Who maintains the ledger? Who has authority over which transactions are valid? And who creates new coins or bitcoins? And who maintains the software? Who can change the rules, etc. A lot of questions, and we will take a look at some. And as I mentioned, this is a peer-to-peer network. It's open to anyone. Anyone can join, and these peers, they reach consensus, and the consensus is well, reached when you have a long enough chain. So this is what it says here: reached by waiting long enough to observe communication confirmations from most of the network. But yeah, so when the chain grows to a sufficient length, and it's you're able to propose values. So this is the mining. It's kind of similar to the leader election protocol that you have implemented. That if you're able to mine a block, then you can propose this block, and in that instance, you are acting as the leader for the Bitcoin network or the blockchain network. Because now you are proposing a value, but you everyone will discard your value unless you are able to mine it. So what happens instead? So now when one user wants to pay to another, he or she broadcasts this transaction to the network. So they are the nodes needs to reach consensus on the transactions that should be included in the block. And well, the important thing is that you must prevent the double spending attacks, so that there is an ordering of these transactions, and no one can spend coins that they don't have. So all the nodes have some rules that they will verify the transactions, and they will put these transactions into blocks. And this is one of the performance things that you will look on. You will see in lab 6 that you can batch a lot of transactions together, which is what is happening in blockchains, that they instead of reaching consensus of every single transaction, it's batched together a lot of transactions in the same block, and then the protocol actually reaches consensus on the entire block instead. So why is this difficult? The nodes, they can be malicious, they can crash, the network can have some imperfections, can have what's it called, partitions or failures, etc. So we cannot use Paxos because it is only crash tolerant, and when we need to handle Byzantine faults, then Paxos is not sufficient. And classical Byzantine fault-tolerant protocols have some problems with scaling, because they're using like MAC or public-private key authentications, and they are susceptible to Sybil attacks. So that's why regular or classical Byzantine fault-tolerant protocols are not well suited for this blockchain application. Yes. So Bitcoin, it introduces the incentive property. And what is the incentive? The incentive is that if you're able to act as the leader to mine a block, then you will be rewarded with some cryptocurrencies. So that's why people are mining, because if they're able to guess or generate these nonce, then they will be rewarded with cryptocurrencies, and this is why it's profitable. And this is also has the advantage that it's increasing the security of the protocol when people are mining. Yes. We can skip this. Yeah, transactions are sent to all nodes. Each node collects new transactions into a block. In each round, a random node broadcasts its block, proposing the next block in the chain. All the nodes implicitly accept or reject this block. And every block contains the hash of the block it extends. So on the step 4 here, nodes will they have typically two rules that they follow. The first rule is that the hash value of the block must be within the target, and secondly, they will always extend the longest chain. So the longest chain here, if we imagine that there's a blockchain here in blue, and then there are forks here with there's one fork at the bottom here with two blocks in pink, and another one with one block on the top. Since this blue chain is longer, then this will kind of be preferred by nodes. Yes. CA here, this is Alice's coin. She signs this. She wants to pay to Bob, and she put this transaction into a block here. But she also tries to pay to herself here. You can see that she already did a transaction to pay to herself, and then she tries to create a fork by paying to someone else. But since this chain is longer, this one will be chosen, but if the one on the top were longer, that will be chosen. Yeah, so I guess now this next figure is kind of flipped around, but for the Bob's point of view, another node, he knows about more blocks in this chain than this double spending attack, which comes on only one confirmation. So since he knows that this chain is longer, he will discard that other block because it doesn't have any children. Yes. So that's the rule of preventing double spending attack. It's to one of the rules is to extend the longest chain. So how it's working in blockchain is that we don't have or Bitcoin, there's no punishment for trying to do this attack, but that attack is in itself a waste of resources, because the resources that was spent to mine this block could have been used to mine an honest block, and if you mined an honest block, then you would be rewarded for that. But the node here that attempted the double spend attack, he has wasted a lot of resources, and he didn't get any rewards. Yes, as I mentioned, that there's the incentive for miners is that they, every time they're able to mine a block, they will receive I don't know what's the current value, if it's been halved already, or if it's still 12.5, or if it's now 6.25. But even if it's 6.25, then if each if each Bitcoin is worth 50 or 60,000, yeah, Vahid mentioned it's 625, then I guess it's you could say it's at least $300,000 that you would get if you're able to mine one block. So all that you have to do to mine a block is to be able to guess this nonce. So if you believe that you're very lucky, you can sit on your own laptop to try to do this, but of course it's very unlikely that you can do it, because there are people that have massive data centers that are mining, and they can run this hash function and a lot or extremely fast. Yes. So yeah, this is how it's the idea is that it will kind of half every 4 years, and at some point it will zero out or cap out, and the idea is that it will transition from miners being rewarded for block rewards to transaction fees. So this is the idea, that on every transaction, then the one that wants to have the transaction processed, they must include a tip to the miners. And if you don't include a tip, then the miners can just discard your transaction, and it will not be used. So yes. I think that we already discussed the proof of work. This is the mining thing. So you mine by creating a block and finding a nonce which hits this target space, and usually the typical thing is to set the target low. So when I mention low, it means that how many zeros is the hash value starting with. So if you're starting with, for example, 3 zeros, then this is higher than starting with 5 or 10, etc. So the more zeros that you define your target as, the more narrow or small this space will be, and it will be more and more difficult to mine. Yeah. So yes, in Bitcoin they want that the average time between blocks is 10 minutes, and they recalculate the target every 2 weeks. So what they do this so that they can change the target depending on how many are mining, or more precise, how much computation is used to mine. So if there's a spike in computational power, then this block time will go down, and the next time the target is recalculated, it is scaled so that the target will be smaller, so that the computational power will on average calculate or generate a block every 10 minutes. You're right. So yeah, when I say computational power, this is also mentioned or described as the hash rate. Yes. So to have a benefit or economic gain from this, then you need to basically consider the hardware and electricity cost, and yeah, other cost of maintenance and placement and heating and everything else. But this is the idea that if it's if the current Bitcoin price or block cryptocurrency price is high, then it will be more profitable to mine. Yeah, so if there's a price drop, then it will not be suddenly it will not be profitable to mine anymore. And yeah, this is why there's more mining going on in countries where electricity is cheap. Yeah. So I guess we mentioned transactions before, but it's yeah, it's a transfer of value from one to another, and these transactions, they are aggregated into blocks, and the way that they are aggregated is through a Merkle tree. Yes. So I hope that's clear. And the miners, they verify that the whole block is valid. So for example, in this case, if Alice had only 25 coins, she cannot spend 17 and 15 and get 5, because it will be like 27. She cannot spend 27 when she have only 25. So a miner wouldn't propose this type of block, because it wouldn't be verified by other ones. So he would waste his computational resources. So yeah. So what happens with the Bitcoin is if Alice has 25 Bitcoins, she wants to send 17 to Bob. She signs this, and she signed 2 transactions. So she signs one transaction with 17 to Bob, and then another one for 8 to herself, because she's spending this transaction, which is worth 25 Bitcoins, and she gets a new address, and the next time she wants to spend, she can send 6 to David, and then she will get she will sign a new transaction that has 2 to herself. And yes, so we can skip this one. Yeah, so Bitcoin, this is of course the first implementation of public blockchain, and there are other ones such as I guess. But there was a slide with some competitors like Ethereum, for example, and other ones that are transitioning away from this proof of work because there are in Bitcoin some throughput limits, and what's often said is that it's 7 transactions every second, and yeah, due to this, it's not scalable solutions for a real world using day to day. And it seems that the one thing that's left out here is the verification time, because if you have a block every 10 minutes and you require 6 blocks before a value is sufficiently confirmed, then it will take way too long for people going to buy groceries to wait for 1 hour before their transactions are cleared out. So that's why there are a lot of new protocols that build some Bitcoins, and also other completely different protocols that are having a different approach. One keyword is off-chain transactions, that you can do transactions that are off-chain, and then they will be added to the chain later on, or what they call like scaling or sharding. They call it sharding, that they will have different smaller blockchains running, and they can later on merge together into one chain, but they are running in a sharded view for performance reasons, and then they can increase all of these limits by a lot. Anyway, I think that was what we managed to do for this hour. Now it's 4 o'clock, and I don't want to keep you more. But yeah, if there's any questions regarding Bitcoin, regarding the project, you can ask, or you can contact me later on, and I will try to answer. So obviously we will not have a lecture on on Thursday or on Monday, because this is Norwegian holidays. So the next lecture date will be 8th, and I will check the lecture plan to see if there makes sense to have any lecture, or if or if not. Anyway, I will update you all. Also, there will not be any labs on the Friday or Monday, because the TAs will also have a holiday. Okay, so that's all for today. So we will see you next time.